So recall up till now, this is what we have done. We had a white elliptic curve and a green elliptic curve, and the coefficients of green elliptic curve are here in green, and we have these isogenies phi and psi. So if you first apply phi and then you apply psi, you go from a white curve to white curve, and this was just multiplication by 2 map. So you take a point here, then you apply phi, you land in green curve, then you apply psi, you again land in white curve, but the isogeny we constructed gave us this p became 2p. Similarly, if you start at the green curve, take a point in the green curve, first you apply psi, you land up in the white curve, then you apply phi, you again land up in the green curve. This is also multiplication by 2. You take a point, this also gets doubled. So this is also 2p. So here you're going from green to green, here you're going from white to white. And we denoted by gamma the group of rational points on the white curve. And finally, to end the proof, we have to show that this gamma over 2 gamma is finite. That is, this index here is finite. But this will be shown in the last lecture. Here we will show that this green gamma over phi of white gamma, this is finite. This is less than or equal to 2s plus 1. So notice that this green gamma is right here and white gamma is right here. So you apply phi to white gamma, it will sit inside the green gamma. So the green gamma is group of rational points on the green curve. You apply phi to this white gamma, it will sit inside the green gamma. Similarly, if you apply psi to this green gamma, it will sit inside the white gamma. So we can talk about this index. So applying phi to the white gamma sitting inside green gamma, so we have to show this is finite. So this is less than or equal to 2s plus 1. And similarly we show this. So this gamma, green gamma, you apply psi to it, sits inside white gamma. So we'll show this is also finite. So what is this S and T? So here S is number of distinct prime factors of this green B right here. And this T right here, this is number of distinct prime factors of this B right here. So notice that the group sitting on top is this white gamma corresponding to this white curve, and here the group sitting on top is green gamma corresponding to this green curve. So we are going to prove this part. So we'll prove this because this isogenies phi and psi are identical. We have seen them, they're dual to each other, and the way they are defined, they are identical. So you can again revisit previous lectures to see how we have defined this phi and psi, and you can see they are identical. So we'll prove this. The same proof will carry over here if you just change green to white and phi to psi. So let us start with the proof. So first thing is we define this Q, this square here. So this is nothing but a group of rational points squared, that is U square, such that U is a rational point. So this is U is could be all the rationals except 0. So these are the units. So this times here represents the units. So we have to inject this group gamma, this group of rational points right here on the white curve. This we will inject into or construct a homomorphism essentially over Q, this group of non-zero rationals over non-zero rationals squared. So this homomorphism will have the following property. So this will be a homomorphism, and this is an important homomorphism. From there everything will follow. So first thing is this group contains a special point because it's just a group of rational points right here. So special points will get mapped to 1. 0, 0 will get mapped to B because this B is precisely this B right here. And this alpha of xy, because this is nothing but group of rational points on the curve, so every point will have 2 coordinates, x and y. So this just gets to x modulo, and obviously everywhere you have modulo this thing because you are going to this group, and this group is just modulo square of rationals, the square of non-zero rationals. So all these are square of non-zero rationals. And for the last part you have to notice that this x is not equal to 0. So this is the big proposition we will prove. So first thing we will show is that the map alpha is a homomorphism. Then the second thing is kernel of alpha is precisely psi of this green gamma. So this is precisely the kernel of the map. So this is how it will inject in. And then we will show that size of this group is what will determine the bound. So let P1, P2, P3 all the way to Pt be distinct prime factors which divide B. That is this B here. Or you can say this B right here. So then the image of this homomorphism alpha is contained in the subgroup here. So this is nothing but repeating the statement, this statement right here. So this consists of elements like this. So this group consists of elements like this: P1 to the eta 1 times P to the eta 2 times P3 to the eta 3, Pt to eta t, where each of this eta is 0 or 1. So it just takes the distinct prime factors of this B, and this group just consists of these elements. And then final step would be to prove that this holds, so that this index here of gamma over psi of green gamma, this is finite. So this is 2t plus 1. So we will start with the most easiest part. This is part number 4. So we want to prove this 4. So first notice this set. So here we are saying eta I can take value 0 or 1. So there are two choices here if eta 1 takes on value 0 or 1. Similarly here there are two choices, and so on here. So you can see there are total of 2 to the power of t choices, and this gamma over psi gamma injects into this group. So the index here has to be less than equal to the size of this group, and this group has at most say 2 to the t plus 1 elements, and this, as we see here, this thing injects right in here. Now we want to prove part 3. So for part 3, on page 72 of the book and in previous lectures, we have shown that, say, if the point x and y lie on our curve C, our elliptic curve C, then x would have the form m over e square, and y would have the form n over e cube. M and e are relatively prime, n and e are relatively prime. So if we show that this m is of this form, plus minus integer square p1 eta 1 all the way to pt eta t, if it is of this form, then we will immediately get this result. So to see this, you know that eta I is 0 or 1. So first take this thing and copy it right here. So alpha xy is x, but x is m over e square. So now you have integer square over e square. If you do modulo this non-zero rational squares, then this portion and this portion cancel out. Only thing would remain is this. So we still need to show that these prime factors actually come from B. So this is what we want to show. These are distinct prime factors dividing B. So how would this come about? So this is what we have done till now. So let us start with our elliptic curve. Y square is equal to x times x square plus ax plus b. Now you plug in the values. For y, you plug in n divided by e cube, and for x, you plug in m divided by e square, and then you clear the denominators. This is what we will get. Now the entire trick lies in focusing on this fact that this side is a square. So left hand side is a square. So therefore the right hand side is product of two integers. One integer is m, and the second integer is this, whose product is a square. So for a second, believe that, you know, m and this second factor, they do not have anything in common. So the m will have, all prime factors will be squares, because you can only then you can take square roots, and these two have no common factors. So you can take square roots only for this m if it doesn't have any common factors. So therefore all the integers here square, which will die if you take modulo rational square, that is modulo units of rational square out. So all these integers are coming from m. Now we have to come to the general case to make sure that where do these integers come from. In fact, they come from B. So we have to show that these come from B. So for this to happen, these two will have to share some common factors. So let d be the greatest common divisor of m, and at the second term m square plus a m e square plus b e4. Now since m and e are relatively prime to each other and d divides m, so d divides m, so d will also divide the second factor. In particular, d will divide, this is addition, so d will divide this, but m and e are relatively prime, so they do not share any prime factor, so d has to divide b. So therefore m and b may share some prime factors. So all the prime factors which come here, because the integer is square here, you have some prime factors which are squares, and those which are not squares are coming from b right here. So all these which are not square are coming from b. So these are all the factors which are coming from b, because these eta I are either 0 or 1. So if they are all 0, that means you just have m as integer square. On the other hand, if they are all 1 or some of them are 0 or 1, they are coming from b. So these p1, p2 all the way to pt are distinct prime factors dividing p. So now we want to show number 2, that is kernel of alpha is psi of gamma, and therefore you will have this map injection. So we have proved in the previous lecture, instead of psi we proved with phi, but as we have talked before, this phi and psi are dual to each other, have essentially the same form. Actually they have identical isogeny form, so we can interchange them. So we have shown this in previous lecture, all these things. So let us repeat it again. So special point lies in psi of this green gamma, 0 0 also lies in psi of green gamma, and this held if and only if b is equal to a square minus 4b of green. So this is a perfect square, but we are more concerned with 3. X y lies on the white curve with x not equal to 0. This lies in psi of green gamma if and only if x is a square of a rational number. So x is a square of a rational number. So if it lies in psi of gamma, it is a square of a rational number. So therefore it will get mapped to 0 right here. So kernel of alpha is precisely this portion. X is a square of a rational number. So in fact we constructed this precisely from this observation. Because we had this observation, we took this x as this, because we know now that this will lie in psi of gamma if and only if this is a square of a rational number, which will give kernel of alpha as psi of gamma. So this is just number 3 repeating itself, nothing much. Now we have to prove one, which is alpha is a homomorphism. So what we need to show is there are 3 points p1 plus p2 plus p3 which go on this O. This alpha of O gets mapped to 1. So what we want to show now is, if this is a homomorphism, then you apply alpha to this. This will become alpha p1, alpha p2, alpha p3, and this should become 1. So this is what we want to show. So this should imply alpha p1, alpha p2, alpha p3 is equivalent to 1 modulo rational squares. So again, p1 is some point x1 y1, p2 is some point which is x2 y2, and p3 is a point which is, this is p2, and p3 is a point which is x3 y3. And you know that alpha of xy is x, so essentially we want to show that alpha p1, alpha p2, alpha p3 is x1, x2, x3, which is somehow equivalent to 1 modulo out this square of these rationals, non-zero rationals. So to proceed like this, you know that when you say you are adding 3 points, this essentially means these 3 points are lying on a line which is cutting the curve. So say this is the line y equals to lambda x plus nu. So this line is cutting the curve, so we plug it into our elliptic curve, which is x cube plus ax square plus bx. So instead of y we put lambda x plus nu, and then you copy this portion right here. So now we expand, put everything on one side, you get x cube plus a minus lambda square x square plus b minus 2 lambda nu x minus nu square. Now this is a cubic polynomial. So this cubic polynomial we can factorize, say x minus x1 times x minus x2 times x minus x3. So you get x1, x2, x3 is nu square. This is right here. And that's pretty much it. You have alpha p1, alpha p2, alpha p3, x1, x2, x3. This is equal to nu square, but this is a square of a rational. So this nu square becomes equivalent to 1 if you modulo out by square of rationals. And that is the end of the proof. So we have a homomorphism. And notice that this x1, x2, x3 are the roots of this polynomial, precisely because once you plug in the line which intersects this curve, that will factorize like this.